On dynamical systems, we now move on to one-dimensional dynamics. And this particular video is on continuous one-dimensional dynamical systems. And of course, as the name implies, we're talking about just one dynamics, talking about maybe just one variable now. So continuous one-dimensional dynamical systems, our goal here is to have a complete qualitative classification of autonomous scalar ODEs. So, for autonomous, we don't have the time component, right? So that takes us back to the idea of scalar autonomous ODEs. A one-dimensional autonomous system has the form dx dt equals f of x, or what you rather call x dot equals f of x, where x is real and f of x is continuous. And it has the following properties. First of all, there is no explicit time dependence, and then solutions never cross, and motion depends only on x. It doesn't depend on time. Then dynamics are determined by equilibria. Okay, so we have an example right here. We have dx dt equals x into 1 minus x, and this is a logistic equation. We've seen this type of equation in previous videos, and then it models population growth with saturation. So the idea of logistic equation is that there's growth up to a point and then it stabilizes. So that's the idea of a logistic growth. Now we go on to have the phase line analysis. A phase line represents motion on the real axis. So the procedure is, first of all, you solve f of x equals 0, and then you determine sine of f of x, and then you draw arrows. So let's see how that works. Imagine this, for instance. You have x dot equals x into x minus 2. This is also logistic in nature. If you equate to 0, first step, solve f of x equals 0. Equate this right-hand side to 0. The answers you are going to get to be 0 and 2 because x is equal to 0 and x minus 2 is equal to 0. So x is 0 or 2. And then if you try to do the sign analysis, you have so you have to consider, you have 0, 2, right? So you're going to consider minus infinity to 0, and then you're going to consider 0 to 2, and then from 2 to infinity. So you want to see whether from minus infinity to 0. Okay, well, I think an easy way to take care of that, right, is to go for Desmos. So you just plot that, and you can see all these ideas straight off. So imagine you have x into x minus 2, x into x minus 2. So as you can see now, so you have 0 and 2 here. From minus infinity to 0, you can see the function is positive. Between 0 and 2, the function is negative, and between 2 and positive infinity, it's positive. So you have positive, negative, positive, and that actually helps like that. So, and that's why you see that for minus infinity to 0, the sign is positive. So the direction is, it's the right hand side. And then from 0 to 2, it's negative. So you have the direction going to the left hand side. So, I mean, positive means that you are moving towards 0. In the first case, like if you look at the graph, positive means you are approaching this 0. Whereas within this interval now, it's negative. So it means you are going back to this 0. So it means you have an arrow going towards 0. You have the on the other side, you have the arrow coming back towards the same 0. Okay, but then 2 to infinity is positive, so it means you have something moving away from that 2 now. You have so this 2 now, this side is positive, so it means the arrow is moving away from 2. So if you look at that technically, it means that from the minus infinity side, you are moving towards 0. From 2, you are moving towards 0, whereas after 2, you are moving away from 2. So at the end of the day, you discover that these two results, which are the equilibrium positions, the equilibrium points, 0 is a you have the two arrows moving towards 0. So it means that 0 is actually some kind of stable equilibrium, whereas 2 is an unstable equilibrium, like that. Okay. So that's a very simple analysis, talking about phase line analysis. So you want to be able to do that with any kind of equation you come across. because that can help you to have some kind of understanding about the nature of equilibria as we see in this case. So to deal with that, right, we just want to do a simple plot. So you want to return the function x into x minus 2. Oh, okay, yeah, that's what we got on Desmos, right? So we're doing the same thing here. So if I just run this now, um, so we are doing it from minus 3 to 5 because from you have 0 and 2, right? So you want to have the negative side there, and then you want to have something less than 0 and something bigger than 2. And you can see this right here now. So this is the curve, This this is the curve right here. So from negative infinity to this place, positive, from 0 to 2, negative, from 2 to positive infinity is positive 2. And then you see that you're moving like this. For this other one, since it's negative, you're going back towards 0 being so 0 here and 2 are points of equilibrium. But then 0 is stable because all the arrows are coming towards it, whereas 2 is unstable because all the arrows are moving away from it. So that's the idea of a phase line function. Now, we then talk about fixed points. Of course, that is already implied in what we just did. So a fixed point x star satisfies f of x star equals 0. Okay, and that's exactly the same thing we did with x into x minus 2. So once you equate it to 0, you now have x star into x minus 2 equals 0. So that means x star is 0 and x star is also 2. So at a fixed point, the solution is constant, and that's how we solve for equilibrium points. So the linear stability now, near x star now, you then have f of x approximately f prime of x star multiplied by x minus x star. And if you let y be x minus x star, then it means that y dot, all right, is equal to f prime of x star multiplied by y. Okay, so we are going to talk about some kind of linearization as we move on. So, and then we already did in a previous video also something about stability classification. So if you get those equilibrium points and you substitute them into the derivative of the function and you get less than 0, that means stability. And of course, I suspect that's what exactly you are going to get. Okay, we have another example here, so let me not do the other one. But if you tried for 0 and 2, you actually see that 0 is stable while 2 is not. Okay, so we talk about stability classification here now. So f prime of x star less than 0 is stable, f prime of x star greater than 0 unstable, f prime of x star equals 0, that's non-hyperbolic, right? So a very good example, you have x dot equals x into 1 minus x. If you solve this, it shows you that x is equal to 0, right? And then x is equal to 1 also. So if you differentiate, this is x into minus x squared. If you differentiate, you get 1 minus 2x. If you put 0 here, you get 1, you see? So when you put 0, you get the derivative gives 1. And that means this 1 is greater than 0. So that means that the equilibrium point 0 is unstable in this case. All right. But for 1, if you put 1 here, you have 1 minus 2, which is minus 1. Minus 1 is less than 0. So that means minus 1 is a stable equilibrium. That's talking about stability. Then we can talk about global dynamics now. So global dynamics, once you get stability at the global level, it means that you don't have to worry about the local dynamics in most cases. In one dimension, every solution converges to a fixed point, and diverges to plus or minus infinity, and it is also constant. So, and there are no periodic or chaotic solutions. So just like we see here now, so the global dynamics here is pointing towards 0 here, as you can see, right? Because everything is pointing towards that 0. Then the other ones are pointing away from it. So that's the idea of global dynamics. A very good example of that we see here. You have x cubed equals, I mean, x dot equals x cubed minus x, because that's the x dt equals x cubed minus x. So you can factorize this now. You have x into x squared minus 1. So that's the same thing as x into x minus 1 into x plus 1. So that means you have minus 1, and set this to 0. You have minus 1, 0, 1, like this. So you can then do the sign analysis. So the sign analysis gives full dynamics of this whole thing. So which we can actually do here too, right? So here we have minus 1. So you have to check from minus infinity to minus 1, from minus 1 to 0, from 0 to 1, and then that can give us an idea. So again, I'll do, we are just doing some kind of qualitative thing. We are not even solving. So x cubed minus x, let me go to Desmos and do x cubed minus x raised to power 3 minus x. So this is what we have right here. So you see, from we have four intervals now, from minus infinity to minus one, from minus one to zero, from zero to one, from one to infinity. So what do we have now? From minus infinity to minus one. Okay, I guess I want to also do this now. Um, okay, I think I get the shape, so I can just try to draw that here. Minus one, zero, one. Okay, so let's come here now. X dots equals x cubed minus x. So if you plot this now, you get something like this. This is minus 1 here. This is 1 here. Okay, I want to try to make it as sensible as possible. So this is this now. And then you have this. So if this is minus 1 and this is 1, okay, this is 0 right here. So the graph itself is like this. You have this coming, this comes through 0 and goes up like this. Okay, so here we have four portions to consider. So we have okay, let me look at how the other one was done just to follow the same thing. Um this one now. Yeah, points. Okay, not this now. Where's that? Okay, I think we're okay. Interval, sign, and direction. Exactly. Interval, sign, and direction. Yeah, that's what I wanted to do. Interval, sign, and direction. So here we can come for this. We have the interval, we have sign, and we have direction. Okay. So in this case, the first interval is from minus infinity. So we have uh from minus infinity to minus one. Minus infinity to minus 1. So in this case now, that means that the sign is negative because, everything is down this way. So the sign is negative right there. I think a better way to even do this will be to use this one. So, so it's down here below the x-axis. So the sign is negative, and then that means the direction will be go is this that is going this way. So it means this is tending towards negative infinity like that. Then apart from that now, we have, okay, I think I want to check something still. Um, I think I did something like this under um, polynomial equations when we're talking about polynomial inequalities, right? So that is very helpful. Then for the next interval, we have done minus infinity to minus 1. Next, we have minus 1 to 0. So this is minus 1, comma 0. So minus 1, comma 0, this is it right here. And this is this region up here. So that is definitely positive. So this is positive. So it means the arrow is going this way. Okay. Then we have the next one. We have the next one now. This is uh 0 to 1. 0 to 1 here is negative. So from 0 to 1, 0, comma 1, that is negative. So the arrow is coming this way. Then lastly, we have 1 to infinity. So 1 to infinity, as you can see, it's above the x-axis. That is positive for sure. So this is positive, and then the arrow is going this way. So if you put everything together now, you have minus 1. Okay, let me change the marker in this case now. So you have minus 1, you have 0, and you have 1. So for minus 1, right? So before for this minus 1, you have the arrow pointing away for the first interval. For the next interval between minus 1 and 0, you have the arrow pointing right. Okay, it's pointing this way, you know. That's minus 1 and 0. Yeah, it's positive, so it's pointing right. From 0 to 1, you have this pointing this way, because it's negative there. The function is negative there. Then the other one, you have this pointing away. So at the end of the day now, you see that in the case where you have something pointing away, so everything is pointing away from minus 1. So this is an unstable equilibrium for sure. Then here now everything is pointing towards 0. So it means that 0 here is stable. Okay. So population dynamics, this means that extinction is a stable equilibrium. It means that the system, when the system goes extinct, it's a guaranteed thing. Okay. And then finally, you have this other one here, which is also unstable because the arrows are pointing away from it. So I think that understanding is really very useful for us in this case. Okay. So sign analysis gives full dynamics, and that's so this the sign analysis is what I've done here now for proper understanding. Okay, then we can talk about structural stability. So structural stability. A system is structurally stable if small perturbations do not change its qualitative behavior, right? So here we have hyperbolic fixed point. A fixed point is hyperbolic if f prime of x star is not equal to 0. So in that case, we have a hyperbolic fixed point. So if f prime of x star is equal to 0, we say it is hyperbolic. And in that case, you cannot really explain, you need more analysis to be able to find out the stability situation there. So a system is structurally stable if all equilibria are hyperbolic and finitely many equilibria exist. That is, you have a finite number of equilibrium points. So we have an example here, x dot equals x squared. Of course, if you equate this to 0 to get the equilibrium point, x squared is equal to 0. That means x is simply just 0. And then if you differentiate that, you get 2x. So f prime of 0 is 2 times 0, which is also 0. So in this case, this system is not structurally stable because now you have uh you have f prime of 0 is 0. Okay. That means the, you have non-hyperbolic fixed point right there, so you can't stock, so the system is not stable for any reason like that. Okay, then we move on to one-dimensional bifurcations. So we have the idea of bifurcations. A bifurcation is simply a qualitative change in dynamics as a parameter varies. So as you vary parameters, the function might vary, and as the variation happens, that's when you talk about bifurcations, right? So maybe within a particular range, the system behaves in a particular way. By the time you change from that system, the behavior changes. Okay, so in this case, we have a bifurcation is qualitative change in dynamics as the parameter varies. The general form is this, that x dot equals f of x comma mu, where mu is a parameter. So as you keep changing mu, then you can see changes. So one kind of bifurcation we can see is what is called saddle node bifurcation. Saddle node bifurcation, that's what you have when x dot is equal to mu minus x squared. So what are the fixed points here? You have mu minus x squared. Okay, I mean, in this case, you have mu minus x squared, right? The fixed points in this case, where you have mu minus x squared. I mean, just equate this to 0. So that means mu is equal to x squared. So take square root of both sides. So you have plus or minus square root of mu equals x. So the, the, the equilibrium points are plus or minus square root of mu. Okay, so plus or minus square root of mu. These are the possibilities you have in that case. And of course, mu has got to be greater than 0, because if it's less than 0, it's undefined. So the condition is that mu has to be positive. So how do we, let's see how that works. So you see, this is actually, the function itself is mu minus x squared. That's what you have right here. So we want to plot x. Now, x is either plus or minus mu. So we want to plot that x, a mu minus x squared against x to see what saddle node bifurcation looks like. And this is it right here. So as you vary mu, mu can take on different values. Okay, we already said that mu has got to be greater than or equal to 0. So, but here still, when mu is 0, you have this value right here. You have this, it's at 0 here. You see this kind of behavior. When mu is 1, you have it going above the line like that. And that is what saddle node bifurcation looks like. Okay, as you vary the mu, you have that parabola increasing and increasing. And then we have, so I think that's the idea of saddle node, right? Then we talk about transcritical bifurcation. Okay, transcritical bifurcation. Okay, I plan to do this before, but it's okay. Um, so for the normal form for transcritical bifurcation, you have x dot equals mu x minus x squared. So in this case now you have a kind of change. So the fixed point, if you solve this, you have x into mu minus x. So you have x to be 0 and you have x to be mu. Those are the two possibilities. And stability is exchanged at mu equals 0. So, okay, trying to see this. Okay, I'm trying to see what I can do with that. Okay, well, I can just quickly just check transcritical bifurcation so I don't take too much time. I wanted to do the code transcritical bifurcation. Okay, I guess we can see the picture somewhere. Okay, maybe I'll just flash something. Right. Yeah, this is what this looks like. The normal form of transcritical bifurcation where R ranges from -5 to 5. So when things get to 0, there's a change. So you have a movement going on like that for transcritical bifurcation. So you have that. So you have a switch over at 0. That's what transcritical bifurcation is about. So that mu now, so whatever you decide mu to be, that's what is going to decide that. So that's for transcritical bifurcation. On the other hand, we have the pitchfork bifurcation. So for the pitchfork bifurcation, you have the supercritical form where x dot is mu x minus x cubed. So if you factorize, you have x into mu minus x squared. So in that case now, your fixed points are, or the equilibrium points are x equals 0 and plus or minus mu. So, and if you do that here, so if we, run that around here, we then have mu now we are taking the value of mu to be from -2 to 2 or whatever else you want to choose. So we have this right here, and then that this gives us pitchfork bifurcation. So this gives pitchfork bifurcation. So as mu is changing, so what is happening? So it gets to a point. So everything keeps going, and then you get to this point, and you have a branching out at a critical point around here. So you have a kind of branching out right here. So that's pitchfork bifurcation. And you can see it's called pitchfork bifurcation because it looks like a pitchfork actually. So we talk about normal forms in one dimension. No, near non-hyperbolic equilibria, systems can be reduced to simple forms, right? Near non-hyperbolic equilibria. So for a saddle node, you have the normal form will be mu minus x squared. For transcritical, you have mu x minus x squared. For pitchfork, you have mu x minus x cubed. Now that this takes us to the some applications of continuous one-dimensional linear system. Um, oh, okay. What happened there? I have to take it back. Okay, I clicked and oh yeah, good. So now we want to look at some applications of continuous one-dimensional linear systems. So for in the first case, we have one-dimensional systems model population dynamics. So one-dimensional system model population dynamics. In models now, we can have logistic growth. Like I said, logistic growth is that situation where you have growth going and it gets to a point because there's a carrying capacity, right? Because there's this K here. So it means there's a limit to which things can grow. It's more like when you culture bacteria in a petri dish. So it gets to a point the population is too large for the petri dish, and then that has some limiting effect. So it means there's a saturation, or when you do chemical reactions to something like that. So this is the equation for logistic growth. So in this case, now if you solve this, you have fixed points at 0 and k. So 0 is that point of extinction of the population, and k is when the population has reached the carrying capacity. And if you do the analysis, you discover 0 is an unstable equilibrium, and k is a stable equilibrium because that's the carrying capacity. And so that's more like when you have uh you have optimal population, if you like. So I can run this code and we can see what this looks like. So you can see this is the equation we are looking at here. Rn into 1 minus zk. So we now fix this R, which is growth rate, and K, which is 10. So this is what this looks like. So you see that whatever is happening, whether the population is coming, so you have the here now we have set the K to be 10, right? K is the what is called the carrying capacity. Okay, I can actually do this. I can say this is n sub 0, and then this is dollar, and then this is dollar. Then I can, okay, alternate shift enter would do the job. Okay, so here now, you see that whether you are coming from below or from above, everything just still goes back to the carrying capacity. So, like I used the example of a petri dish the other time, right? Or even if it is human population. So once a place is over congested, right? People can start moving out of the place. The place becomes unbearable, and people have to move out. At the end of the day, everything comes back to the carrying capacity. And if you also look at the example of a petri dish, right? So you are culturing bacteria. When you started out, you started with a number of bacteria that maybe one quarter of the population. After some time they start growing so much that they they reach the saturation point. Okay, so depending on the initial condition, so if the initial condition is 1, it grows and then stabilizes. If it's 5, it grows and then stabilizes. If it's 15, which is above the carrying capacity, the population will have to find a way of adjusting and then balance out. I mean, it reminds me of the Chatelier principle in chemistry, that things systems have a way of finding a balance at the end of the day. So that's the idea of logistic growth. So a saturation is reached ultimately, right? So that is the idea of logistic growth. And then we have what is called the alley effect. So in this case now, there exists a threshold population A. Below A, extinction occurs. All right. So for alley effect, now it means you need, okay, maybe I should even look for alley effect in layman's term. Alley, alley effect, alley effects in layman language, in layman terms. Okay, good. Alley effect. Okay, good. In simple terms, the alley effect is an ecological phenomenon where a small population of animals or plants struggle to survive and reproduce because its number are too low. So the idea of alley effect is that it's more like in business too. There's a number of goods you have to sell for you to actually break even or for you to be able to thrive in business. So once you don't reach that, there's extinction occurs, right? So that's the same thing about alley effect in population dynamics. So there's a threshold population. If that population is not reached, then there's extinction of the population. Okay, so it means that you need a number of individuals of a particular species for you to be able to sustain the population. If that number is not reached, then the population dies. So we have this whole Python code here, and then I'll just run it, and you can see this whole thing here. And that A is the threshold. So look at what we have here now. So there's a threshold A. Okay, we have the threshold, which is around this place, and then we have the carrying capacity up here. All of that has been fixed because so carrying capacity here, it has been fixed as 10. The threshold has been fixed as 3.0. So you have the early threshold as 3, the carrying capacity as 10, and the growth rate is 1. So it's more like you have should I we say kind of steady growth rate or something like that. Okay, so and this is the function itself representing early effect. So in this case now, so this is the early threshold right here, this 3 here. So any population that's not at least 3, that doesn't get to 3, will die out. So this one is starting from 2 now, it just dies off. This one is starting from less than 2, it dies off. But then anything from this early threshold upwards, like in this case now, you have population starting from, okay, here we actually had 0 0.5, and then we had 2, and they die out because they don't get to 3, which is the early threshold. On the other hand, we have this starting from 4, higher than the early threshold. Of course, in that case, logistic growth will now affect it, because if you look at the expression, we still have this 1 minus nk is what represents the logistic, because k is the threshold, the carrying capacity. That is the maximum capacity of the accommodation, if you like, or of the space for the population. And then here now we have so if you remove n minus a here, it's back to logistic growth. But with n minus a now, you introduce the early effect, you introduce a threshold where below it nothing, the population cannot thrive, but above it the population grows and reaches the carrying capacity, like that. So that's an interesting idea in population dynamics, talking about the early effect. Then we also have the harvesting model. The harvesting model is basically like it's basically the logistic growth with harvesting. So it's more like imagine you have a fish pond, right? And of course, the fish pond has a carrying capacity K because it can only take so much fish depending on the size of it. Okay, so let's assume that all the fish they grow up, they keep growing and growing, but then from time to time, maybe after every 1 month or something, depending on whatever your harvesting schedule is. So you go there to harvest some fish. So this is this H now. So you're taking this H out of it. So in that case now, even so it means that the system never really reaches saturation because when it's near maybe even when if it reaches saturation, you get there and harvest, then you set the system to keep growing again, right? So and then I mean this idea is very important in fish management, right? Like for people who are into fisheries and everything. So this is a system you can use the system to manage how often and how much fish should you harvest to ensure to have a sustainable fish pond, right? So this is what this harvesting model does. So this model exhibits saddle node bifurcation, like we saw before. So in this case now, of course, there's still everything. It's like logistic in addition to you harvesting from time to time. So then we set up this system, you know, and then you may want to look at the code later if you wish. Um, if you want the notes, I can send it to you, especially if you're a member of the channel. Right. So see what happens here. So we have so we see first of all here you see the critical there's a harvest rate here. We need a critical harvest rate which is at 2.5. So at 2.5 harvesting so if you harvest above that, it can lead to trouble. So in this case now, we have the time of evolution of the harvested logistical model. So at H now, H is 0.5. So if you harvest at 0.5, you still have the population growing. Then if you harvest at 1.5, the population still grows and stabilizes somewhere. It is still logistic, right? But if you harvest at 2.5, okay, in this case now, it can lead to some decline. So you have to be sure that so if you don't want the population to go extinct, maybe if you harvest more than 2.5, the population can go extinct. Now this one is still it's not increasing, right? But at least it still stabilizes somewhere and you still have some population surviving. So we have that critical harvesting rate at 2.500 like that. Okay. So this can actually help you to make such decisions as to when to harvest, how to harvest, and things like that. Okay. Yeah. So with that in place, we then have the phase functions, right? We talked about the phase functions the other time. So you have the growth rate on the x-axis, and you have the population on the y-axis, and you have the phase lines drawn there. Then we have a saddle node bifurcation, right? Like, you know, these are different equilibria. Okay. So, if you harvest above 2.5, right, you are going to cause, you're probably going to have a kind of extinction of the population, right? But I mean, you have this, if the harvest rate is zero, okay. If the harvest rate is zero, see what happens. You have the stable equilibria here, you have unstable equilibria here, and HC here is the 2.5. That's the critical harvesting rate. Yeah, that's the critical harvest rate right there, like that. So we have this kind of saddle node bifurcation, like we saw the other time. Okay, so and then of course we have some equilibria right here. H is 0.5. We have increase, we have this going, and we have this like this, some kind of analytical expression for that. Okay, so complete classification procedure in short for continuous one-dimensional system. What do? Given x dot equals f of x, first solve f of x equals 0 to get the equilibrium point, compute f prime of x star see uh, which of the equilibrium points are stable, and then you can draw a phase line, to know which one is where are the lines going, and then you can determine the global behavior ultimately, right? So, in summary, we then have this. In summary, we then have that this if for equilibria we solve for f of x equals 0. For stability, we differentiate f of x to get f prime of x and evaluate f prime of x at the equilibrium points we found there. Then you can then get the dynamics by drawing the phase line. So this tells you which point is stable, which point is not stable, and then you have bifurcation. Bifurcation, you need the parameter to know how bifurcation goes, and then for robustness, you have to talk about the hyperbolicity of your system. Then some key results. There's no chaos in one dimension. All right, and no periodic orbits in this case for one-dimensional continuous system, that is. Then complete classification is possible. Only three generic bifurcations are possible, like what we saw. We saw pitchfork bifurcation, we saw transcritical bifurcation, and saddle node bifurcation. And then there's hyperbolicity, which implies robustness. Okay, so the concept map goes like this. You have ODE, ODE. From ODE, you get the fixed points, you evaluate the fixed point for stability, and you draw your phase line. And then that can lead to bifurcations, normal forms, and then you can have some applications like we found for population models, right? So we then have some practice problems. You want to try your hands on them as much as possible. So solve all problems carefully, show all steps, including phase lines and stability classification. Consider the system x dot equals x squared minus 4. Find all fixed points. Of course, it's clear x minus 2, x minus x plus 2 equals 0. So x is minus 2 and plus 2. Determine their stability. So you have to do the sign thing like I did the other time. So you have minus 2 and 2 now. So you have minus infinity to minus 2. What's the nature of that? From minus 2 to 2, what's the nature? And from 2 to positive infinity, what's the nature? Then you can sketch the phase line based on that. Then you can do the same for this logistic type equation right here. Find equilibria, classify the equilibria. The equilibria here will be 0 and 3 from what we can see. Then describe the long-term behavior of x of 0 greater than 0. Okay. Then we have 3 and 4 here. Now, 3 and 4, we have a cubic system. Again, x dot is x cubed minus 3x. Find out fixed point, just equate to 0. So you have x into okay, x into x squared minus 3. So you're going to find all that and determine the stability using f prime of x and describe the global dynamics. You can determine that. Structural stability, you can also do the same for this. Then questions 5 and 6. For question 5 and 6, okay, you're going to see all the saddle node bifurcation, transcritical bifurcation, and then you can even use Python. You can sketch, actually, you can also sketch, right? You can sketch the bifurcation diagram to see what that looks like. And then we have the pitchfork bifurcation and harvesting model, like I showed you the other time. Now, this is a harvesting model. Okay, yeah, same as n over k, right? Except that here, maybe we take that the k is actually 1, we take the carrying capacity to be like maybe 1 unit, if you like. Then find equilibria in terms of h. So again, you still equate to 0 and find solve for n, and then you get the points of equilibria. Then determine for which values of h extinction occurs. So which h is going to lead to extinction. You determine that, and then identify any bifurcations for sure. So, and then we have 9 and 10 now. Global behavior. Find all equilibria equal to 0, of course, and find all the values of x. Determine the sign of dot x. So you are going to find the overall sign of this whole thing. Then describe the global behavior of of solutions. Then you have Ali effect right here. Here now. So this is the Ali part now. So it means that the Ali threshold is 2. And then, of course, this is the logistic part right here. So you want to find all equilibria, determine their stability, interpret the biological meaning of each equilibrium, and sketch the phase line. So with this, I come to the very end of this interesting video about continuous one-dimensional dynamical systems. We've seen how to classify all these things, how their bifurcations also occur. Let me know how helpful this is for you. And if there's something else to let me try, feel very free to let me know. If you have subscribed already, I must thank you very much for doing that. If you have not, of course, you don't want to keep missing out on this very sweet mathematics. So why not subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel, and that comes to some special privileges, right? You can have access to the PDF notes I'm using. You can have access to even the raw code sheet where you can interact with the codes and things like that, and so on and so forth. All right. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.